Hello students, welcome to EPG Patashala. I am Dr. Gayatri, Assistant Professor in Center of Advanced Study in Crystallography and Biophysics, University of Madras. Today we are going to discuss about a module, powder diffraction, under the paper Biocrystallography. The objectives of the module are we will have an introduction to powder X-ray diffraction, how the powder X-ray diffraction data looks like, and the method generally called as a ritual refinement, how it is used to refine the structure, what are the applications of X-ray powder diffraction, and finally what are the strengths and limitations of X-ray powder diffraction. Powder diffraction is one of the most important, powerful and widely used analytical technique for characterizing the materials. This technique helps for a wider investigation of physical, chemical and even mechanical properties of materials. Powder diffraction method was first devised in the year 1960 by Debye and Scherer independently and by Hull in the year 1917. The technique developed steadily. The traditional applications like phase identification, determination of accurate cell dimensions, and also in the analysis of structural imperfections. Crystallographers generally use single crystal diffraction method to determine the structure. But if single crystals of appropriate dimension didn't grow, then one goes for the powder diffraction. Those who do crystal growth research, powder diffraction is a kind of a standard technique to index the various planes. For structural studies, single crystal X-ray diffraction often thought to be the synonymous for several decades. Powder diffraction has made important contributions to the understanding of materials, structure and also their behavior. However, it is perhaps in the past few decades that has seen some of the most remarkable breakthroughs in experimental powder diffraction and in the analysis of powder diffraction data. Instrumentation has become increasingly versatile to the extent that high throughput and resolution are no longer mutually exclusive. In the field of data analysis, indigenous algorithms help in characterizing, solving, and also in refining the structure of molecules. In the case of a powder diffraction method, a single wavelength of collimated X-ray beam is incident on the powder. The diffracted beams are subsequently absorbed by the detectors. The resulting diffracted beams can be measured and the corresponding despacings are calculated. The final results are generally given as intensity versus despacing or intensity versus 2 theta. Modern diffractometers are the computer controlled, which allows for fast and efficient data collection and also in the data analysis. Let's see the experimental methods in X-ray powder diffraction. To obtain X-ray diffraction data, the diffraction angles of various cones 2 theta must be determined. The main techniques that are used are Debye-Scherer camera, which is a photographic film, or we can use a powder diffractometer. This figure shows one plane in the given HKL set and the diffracted beams formed. More than one powder crystallines may be so oriented that their HKL planes make the correct Bragg angle for the reflection. If this plane is now rotated about the incident beam as the axis of rotation in such a way that the angle is kept constant, then the reflected beam will travel over the surface of a cone where the axis of the cone coincides with the transmitted beam. Though the rotation doesn't actually occur in powder method, the presence of large number of crystallines in the powder sample having all possible orientations is equivalent to this rotation. This happens because of certain fraction of the particles whose HKL planes make the correct Bragg angle with the incident beam and which at the same time lie in all possible rotational positions about the axis of the incident beam. For example, in powder diffraction, each tiny crystal is in different orientation. Because we have so many tiny crystals which are randomly oriented, just by chance, few of these crystallines are correctly oriented for the diffraction. Therefore, every set of lattice planes will be capable of diffraction and there will be the formation of cone of diffracted radiation. In short, we can say that when X-rays fall on a powder sample of tiny crystals in all orientations and the diffracted beam of each order HKL will form a cone. Separate cone will be formed for each set of differentially spaced lattice points. A circle of film is used to record the diffraction pattern. Each cone intersects the film, giving rise to diffraction lines. The lines are seen as curves or arcs on the film unless they occur exactly at 2 theta equal to 90 degrees. In that case, they appear to be straight. From the measured position of given diffraction lie on a film, theta can be determined, and by knowing the wavelength, one can calculate the spacing d of the reflecting lattice planes. When the film is removed from the camera and processed, we will observe that the diffraction lines and the holes for the incident and transmitted beams will be seen. There are always two arcs in the X-ray beams, K alpha and K beta. This causes the highest angle back reflected arcs to be double. With the help of this information, it is always clear that which hole is for the incident beam and which is for the transmitted beam in the film. So in single crystal X-ray diffraction, we have to actually rotate the crystal with respect to the incident beam so that a particular set of HKL planes make the correct angle with the incident beam so as to satisfy the Bragg's law. Whereas in crystalline powder, since it contains large number of small crystallites, each of which is randomly oriented. At any one time, all the allowed HKL planes will be correctly oriented in the X-ray beam and they satisfy the Bragg's law of diffraction. For every possible HKL, some crystals will make the correct theta for the diffraction to occur. The scattered intensity is usually represented as the total number of accumulated counts. It is measured as a function of 2 theta. Powder diffraction provides information not only about the atomic structure but also other properties of the materials like particle size, size distribution, stress, strain, texture, and so on. In powder sample, crystals will be in random orientation and the goniometer swings through many angles. So we have enough small crystals in a powder sample, enough angle so that we can get enough diffraction to determine the properties of the material and structure of the material. Powder diffractometers generally use the Bragg-Brentano geometry. Here the incident angle is theta, which is defined between the X-ray source and the sample. The diffracted angle is given as 2 theta. It is defined between the incident beam and the detector angle. The incident angle theta is always half of the detector angle 2 theta. So in a theta 2 theta ratio instrument, the tube is fixed. The sample rotates at theta degrees for 1 per minute and the detector rotates at the rate of 2 theta degrees for 1 minute. In a theta theta instrument ratio, the sample is fixed and the tube rotates at the rate of minus theta degree per minute and the detector rotates at the rate of theta degree per minute. The information provided in a powder diffraction pattern consists of peak position, peak intensity, and peak shape. Peak position depends on the lattice dimensions, that is A, B, C, alpha, beta, gamma, and also the space group. Peak intensities generally depend on the distribution of the atoms within the unit cell. For example, the atomic parameters X, Y, Z, and the thermal factors, etc. Difference between the peak intensities that are recorded with a single crystal and a powder sample is that the total number of Bragg reflections will be up to 4,000 to 5,000 in the case of a single crystal and only to a maximum of 20 to 30 lines in a powder pattern. Peak shapes are the convolution of instrumental parameters and the microstructure of the sample. It tells the information about the crystallinity, disorder, defects. Powder diffraction generally doesn't provide this information straightforward because a powder diffraction data set is a one-dimensional projection of the three-dimensional reciprocal space. It gets increasingly overlapped at increasing to theta. Even though overlapped, the powder diffraction pattern contains the same information as a single crystal dataset. In the case of a powder diffraction, the question is how to deconvolute it. In the year 1960s, Hugo Rietveld introduced a whole pattern fitting structure refinement method, which is generally known as a Rietveld method. It is used to deconvolute the powder diffraction pattern in order to retrieve the individual intensities. It is an important step towards extracting the three-dimensional structural information from the one-dimensional powder diffraction pattern in order to study the structure of the crystalline materials. Similarly, techniques which doesn't involve the structural data have been introduced for modeling powder diffraction patterns to also extract various parameters like position, breadth, shape that defines the individual reflections. These are used in most applications of powder diffraction and are the basis of new procedures for characterizing the microstructural properties of the materials. Many subsequent advances have been based on this concept, and powder diffraction is now one of the most widely used technique that is available to material science researchers to study the structure and microstructure of crystalline solids. The basic idea behind the Ritweil method is to calculate the entire powder pattern using a variety of refinable parameters and to improve a selection of these parameters by minimizing the weighted sum of square differences between the observed and calculated powder pattern by using least squares refinement method. Hugo Ritweil, who invented the method a few decades ago, he used it to extract as much information as possible from a powder pattern. At the very beginning, this was mainly restricted to atomic positions from neutron diffraction patterns. There will be much more information hidden in the powder pattern, which may be subjected to Ritweil refinement. Simultaneous Ritweil refinements of several data sets, for example, can be used for full texture analysis also. Fast detectors like image plate detectors, in combination with powerful microcomputers, reveal a new aspect of Ritweil refinement with time dependence. By recording full powder patterns in a short time interval, the change of the crystal structure in dependence on pressure, temperature, or during a chemical reaction can be monitored, and the dynamical processes can also be visualized. Ritweil method is a least squares procedure, and the minimized quantity is given in the formation S is equal to summation of Wi and the square of the difference between the observed and the calculated intensity. In this equation, W is called as a weight factor. It is based on the counting statistics. The calculation of the parameter S gives a quantitative estimate of the matching between the observed and the calculated data. Ritweil method is based on the assumption that the measured diffraction pattern is generally represented as the intensity versus the scattering angle 2 theta, which can be approximated by the analytical expressions containing the instrumental and the structural parameters. The contribution to the calculated intensity of the ith data point, which is represented by YCI from the Bragg reflection, diffraction optics effects and the instrumental factors can also be expressed by this equation, where S is the overall scale factor that depends on the amount of a specimen irradiated by the X-rays. It depends on the intensity, on the optics used, and also on the quantum efficiency of the detector. H indicates the Miller indices for the Bragg reflection. L contains the Lorentz and polarization factors. MH is for the multiplicity factor. FH is a structure factor for H, the Bragg reflection, and phi is a profile function where in this equation 2 theta I is corrected for 2 theta 0 error. pH indicates the preferred orientation function, which accounts for non-ideal distribution of the crystalline orientations, leading to a systematic enhancing of peak intensities of certain class of reflections. While studying the surfaces of metals, this effect is often referred to as a texture. The absorption factor is included as A, that depends on the thickness of the sample. It depends on the geometry, that is the diffraction geometry, and it also depends on the actual weighted average linear absorption coefficient. YBI is a background value for the ith data point. Bragg reflections contained in this summation at each point of the powder pattern are determined from the sorted list of possible reflections and their profile width at 2 theta. The structure factor equation contains the structural information as it is given here. Fj is the scattering factor or the atomic form factor, which is generally corrected for real and imaginary terms of the jth atom. G is the occupancy factor. The fractional atomic coordinates of the jth atom are given as xi, yi, and zi. Temperature factor coefficient is given as Bg. Numerical criteria of fit that is used in Ritweil method and other pattern fitting procedures are given here. There are different types of pattern fitting procedures. We have R pattern, R weighted pattern, R Bragg factor, R structure factor, goodness of fit indicator, where Wi is the observation weight, N is the number of observations, P is the number of adjusted parameters, and C is the number of constraints that are applied. Red-wheel method requires the digitized data and the knowledge of approximate structure model. A number of other starting parameters can be guessed by visual inspection like the background coefficient, zero angle, and so on. The most reliable values which can be obtained by standard red-wheel approach are probably the lattice parameters since they are less biased by errors in the structural model. For the three-dimensional structure determination, by using X-ray powder diffraction, there are certain limitations in the red-wheel method. Total number of atoms in the molecule has to be around 30. The computer program SARPAW is used to obtain the molecular structure from the powder pattern. This program is given by Professor Giacavazzo and their group from the University of Bari. Position of Bragg peaks are the function of wavelength and the interplanar distances, that is the d-spacing. D-values and Bragg angles vary discontinuously as the function of Miller indices and the unit cell dimensions. Figure A shows the discontinuous distribution of Bragg angles using short vertical bars of equal length. That is, only Bragg peak positions are represented by the vertical bars of equal length. In figure B, the intensities are represented with bars of variable lengths. Higher the intensity, the longer will be the bar. In figure C, the peak shapes are indicated by convoluting individual intensities with appropriate peak shape functions, and a constant background has been indicated by the dashed lines. The final diffraction pattern is the sum of all the components as indicated in figure C, which includes Bragg peak position, intensity, peak shape, and background function. The determination of crystal structure from the powder diffraction data is inverse process and it's much more complex. First, individual Bragg peaks should be located on the pattern, and both their position and intensities have to be determined by fitting to certain peak shape function including the background. The second step, the peak positions are used to establish the unit cell symmetry, parameters, and the content. Third, the peak intensities used to determine the space group symmetry and also the coordinates of the atoms. Finally, the entire diffraction pattern is used to refine all crystallographic and peak shape function parameters including the background. Let us recollect the Bragg's law. If the path difference between X-rays scattered by two planes is an integral multiple of wavelength, then it leads to a constructive interference. Now consider the incident rays make Bragg angles only slightly different from theta b, then we observe that the destructive interference is not complete. It is observed that the diffracted intensities at angles near to 2 theta is not 0, but it has a value intermediate between 0 and the maximum intensity of the scattered beam. The width of the diffraction curve increases as the thickness of the crystal decreases. The width B is measured at an intensity equal to half the maximum intensity. X-ray powder diffraction can also be used to distinguish between the allotropes of the diamond and graphite. The position and intensities of the peaks are also used for identifying the underlying structure of the material. For example, here the diffraction lines of graphite would be different from that of diamond even though they both are made up of carbon atoms. This phase identification is very important because the material properties are highly dependent on the structure. Powder diffraction data can be collected by using either reflection geometry or by transmission geometry. Because the particles in the powder sample are randomly oriented, these two methods will reveal the same data. Let's see the various ways to prepare the powder sample. First is a top loading a bulk powder into a well. So in this case, we have to deposit the powder in a shallow well of a sample holder. Using a slightly rough surface to pack the powder will help in minimizing the preferred orientation. Mixing the sample with filler such as the flour or glass powder will also help to minimize the preferred orientation. Powder may need to be mixed with a binder to prevent it from falling out of the sample holder. Or the well of the sample holder can be coated with a thin layer of Vaseline. And the other method is dispersing a thin powder layer on a smooth surface. A smooth surface such as a glass slide or a zero background holder may also be used to hold a thin layer of powder. In the case of a glass slide, Glass will also contribute an amorphous hump to the diffraction pattern. The zero background holder avoids this problem by using an off-axis cut single crystal. Dispersing the powder with alcohol onto a sample holder and then allowing the alcohol to evaporate results in even coating of the powder that will adhere to the sample holder. Powder may be gently sprinkled onto a piece of double-sided tape, or a thin layer of Vaseline can also be used so that it will adhere to the sample holder. The double-sided tape will also contribute for the diffraction pattern. For preparing a powder specimen, we need an ideal powder sample that should have many crystallites in random orientation. The distribution of orientations should be smooth and it should be equally distributed among all orientations. If the crystallites in a sample are very large, there will be not a smooth distribution of the crystal orientation, so one will not get a powder averaged diffraction pattern. Crystallites should be at least less than 10 micrometer in size to get good powder statistics. Large crystallites and non-random crystallite orientations both will lead to peak intensity variations. The measured diffraction pattern will not agree with the expected from an ideal powder. The measured diffraction pattern will not agree with the reference patterns which is stored in the powder diffraction file database. These methods are necessary for mounting small amounts of powder. The methods help elevate with the preferred orientation. The constant volume assumption is not valid for this type of sample. So quantitative and Ritfield analysis will require extra work and may not be possible. Some of the important characteristics of samples for the X-ray powder diffraction. A flat plate sample for X-ray powder diffraction should have a smooth flat surface. If the surface is not smooth and flat, X-ray absorption may reduce the intensity of low angle peaks. Parallel beam optics can be used to analyze the samples with odd shapes or with rough surfaces. And densely packed, randomly oriented crystallites, grain size should be less than 10 microns. These are some of the characteristics one should follow. Now let us have a look on the interpretation of powder X-ray diffraction data. The crystal lattice type cell parameter information can be obtained from the number and the position of peaks. The type of atom and position of atoms can be retrieved from the intensity of peaks. The other informations can be obtained from the powder diffraction data, that is, we can identify the unknown phases, we can determine the phase purity, determination and refinement of lattice parameters, investigation of the phase changes, we can also solve the structure, and we can determine the crystallite size. Moving on to the determination of an unknown material, we have to obtain few tens of grams of the material as much pure as possible, grind the sample to a fine powder, typically in a fluid, to minimize inducing extra strain that can offset the peak positions and also to randomize the orientation. Powder less than 10 micrometer in size is always preferred. The next is the despacing of each peak is then determined by obtaining the solution of the Bragg equation for the appropriate value of wavelength. Once all despacings have been determined, automated search or match routines will compare these of the unknown to those of the known materials. Because each mineral has a unique set of despacings, matching these despacings provides an identification of the unknown sample. The systematic procedure is used by ordering despacing in terms of the intensity, beginning with most intense peaks. Powder diffraction data of the known compounds have been compiled into a database by the Joint Committee on Powder Diffraction Standards. Many other sites contain despacing of minerals, such as the American Mineralogist Crystal Structure Database. Commonly, all this information is an integral portion of the software that comes with the instrumentation. This slide shows an example of the powder diffraction file. It contains all the information of the despacing, the intensity, HKL planes, the molecular weight of the compound, what system, space group, what are the cell parameters. We can obtain all these informations from the PDF file. X-ray powder diffraction data pattern is considered as a fingerprint. It can be used to identify the compound. One of the major application of powder diffraction is in the identification of the compounds in kidney stones. The figure shows the powder diffraction pattern with different D spacings. The scale of plot is the intensity peak on the y-axis, and on the x-axis it is 2 theta. The two examples given here are uric acid and wavelite. These are the compounds identified in the kidney stones using powder diffraction pattern. Moving on to the strengths and limitations of X-ray powder diffraction, let's see what are the strengths of X-ray powder diffraction. It is very powerful and rapid technique for identification of unknown materials. In most cases, it provides an unambiguous mineral determination. Minimal sample preparation is required. Data interpretation is relatively straightforward. And moving on to the limitations, homogeneous and single phase material is best for identification of an unknown, which is a bit difficult to attain. Must have access to standard reference file of the inorganic compounds, which stores the D spacings and the HKLs as a standards. For unit cell determinations, indexing of patterns for non-isometric crystal systems is much complicated. Peak overlay may occur and it will again worsen for high angle reflections. Moving on to the applications, X-ray powder diffraction is most widely used for the identification of unknown crystalline materials, say for example minerals and inorganic compounds. The determination of unknown solids is very critical to studies in the biology, environmental sciences, geology, material science, engineering, and in many other fields. Other applications include the characterization of crystalline materials. It is used in the identification of fine-grained minerals. It is used in the determination of unit cell dimensions and also to check the sample purity. Powder diffraction has several advantages as we saw. It also has other advantages. It is used in solid state and material science as an analytical tool, as a qualitative and quantitative analysis. It is used to determine the relative amounts of phases in a mixture by referring to the relative peak intensities. Unit cell parameters and Brevis lattice symmetry can also be obtained. It is also used to study the residual strain. The structure of the molecule can also be solved using the Ritchfield refinement of the entire diffraction pattern. X-ray powder diffraction pattern also reveals the texture and epitaxy of the sample. It is also used to study the crystallite size and the microstrain, which is indicated by peak broadening. Powder XRD is also used to study other defects like stacking faults, etc., that can be measured by analysis of peak shapes and also by using the peak width. Certain in situ experiments can also be done that will reveal the properties as a function of time, as a function of temperature, and the gas environment. It is used in textural measurements such as the orientation of the grain and also in a polycrystalline sample. So students, let us summarize what we have learnt in this module. The module deals with the introduction of powder X-ray diffraction, which is one of the most widely used analytical method to study various properties of the materials. The module also throws light on how to and in what cases the powder diffraction can be used. The conditions and methodologies to be followed in X-ray powder diffraction are detailed in this module. The applications of powder XRD are discussed along with the strengths and the limitations of this technique. Thank you very much for watching this video.